So hello everyone. So in last class we were discussing about this Hopfield recurrent network. We took one example how to solve problem on this. So in general it's feedback kind of a network. You can remember that there is no self feedback. So there is no self feedback and weight matrix is symmetric. So these are two important things that one should remember about Hopfield network. Then we saw this energy gradient, and incremental energy is reducing with respect to time. So as time progresses, like this energy of this network will keep on reducing and it will settle to some point. Okay, so it will settle to a minima, energy minima, and there onwards there is no say decrement of the energy. It will remain as it is, and that point of the uh, machine is supposed to be storing the expected vector which I want to store. So that means one should create minima at desired location, desired vector location. Then we took an example that this was given to us and there were no threshold or external inputs, and find energy function. So we could find out with the help of energy function. So that is minus half V transpose W V. So you just multiply these three things, you will get this energy equation, and then we put all possible values of V's. Because V is a binary thing, we can take +1 or -1. So there are 4 bits with us. That means 2 to the power 4, 16 possible states are there in this machine. So for each combination of V, that is from -1, -1, -1, -1 to +1, +1, +1, +1, there are 16 states. We find out energy. So in this case, the energy was -6, 0, and 2. So minimum possible energy in this network is -6. The key thing one should remember when you go with Hopfield is that uh, the updation sequence is random and only one node is allowed to update its value at a time. Okay, say there are 4 nodes in this circuit, then you decide one sequence at the beginning that I will follow. Suppose I am here following 1, 2, 3, 4, then only this neuron, that is neuron number 1, is allowed to update its position or output. Then the remaining 3 things will maintain their outputs. And in the second step, this neuron is allowed to update its output and other neurons are kept as it is. So like this, the updation will be carried out. Only one neuron at a time. And in the derivation, we have proved that if I follow such kind of update, asynchronous update, then energy is reducing for each step, or at the most it is maintained. So basic thing is that it will not grow, and then system is not unstable. So system is stable. Now next point is how to store patterns. So assume that bipolar binary prototype vectors are with us and there are say m such or p such vectors we want to store. Say there are s1, s2 and so on up to sp. So these are the vectors we want to store in the auto associator. So simple thing is use this storage algorithm. So what is storage algorithm for this network is this simple formula. What this means is you take the prototype, say suppose S1, you multiply with S1 transpose, so this will be an outer product, plus take the second pattern, you multiply with its outer product, plus and so on up to SP, that is pth pattern. So this will be a matrix, and subtract P into I. I is identity matrix, so P is the number of patterns. So you will find that when you do the calculation here, okay, so the diagonal elements are all ones for each of this product, because this is just like a square, so square of -1 and square of +1 is same, that is 1. So on the diagonal you will find all elements are 1 and all elements, that is 1, are added p times. Okay, so there will be a sum of the diagonal of these ones is p. And what we do, we take identity matrix, that means all elements other than diagonal are 0 and on the diagonal it is 1. So when I multiply with this by p, so this will be p, p and so on. So diagonal will be p and diagonal of this summation, outer product summation, is also p. Okay, so when I do this subtraction, the diagonals will be made 0. Now why I want to do like that? Because there is no self feedback. Okay, to do that I just make those connections 0. Okay, so this is very simple. You take S1, you take S1 transpose, you take S2, you take S2 transpose. So this is second pattern that I want to store in the network. You keep on doing like this up to P patterns and then just subtract number of patterns multiplied by identity. That's it. So this will give you final weight matrix for your problem. Okay, so let us take one example how we can do this, how we can design an Hopfield neural network. So here, let us say I want to store these two patterns in the network. So count how many numbers I want to store. So there are 4 elements in S1. That means my network is having 4 neurons like this. Then I should have some input nodes, and you can see that there is a feedback like this. Okay, so this is node 1, node 2, node 3 and node 4. Then you have connection here. So don't draw a self feedback. So there is no connection from say this node to this fourth node itself. You just skip that. So this will be my circuit. Okay. Now thing is I want W here so that this will work. Now how to do that? So W is equal to summation I equal to say or M equal to 1 to P, and it is Sm into Sm transpose minus P into I. Okay, so that we have to do. Now here P is equal to 2. That means I just need to store 2 patterns. So what is to be done? You take first pattern, say S1. I am preparing outer product for S1. So this is S1. It is minus 1, 1 and 1 multiplied by its transpose. So this will result into a matrix. You take this minus 1 and multiply with this vector. So it will be plus 1, plus 1, minus 1, minus 1. Then you take this minus 1, second number, multiply again. So it will be plus 1, plus 1, minus 1, minus 1. Then you have minus 1, minus 1, 1, 1. Again minus 1, minus 1, 1, 1. So this is the outer product due to pattern number 1, that is S1. Then you take second pattern. So second pattern is minus 1, 1, 1, minus 1. You take outer product. So it is plus 1, minus 1, minus 1, plus 1. Again, take second number here. This is 1, multiply with this vector transpose. So it is minus 1, 1, 1, minus 1. Then minus 1, 1, 1, minus 1. Last one, it is plus 1, minus 1, minus 1, plus 1. Now this is due to pattern number 2, that is S2. Now we have to add these two matrices. Okay, so this will be so this is 2, then I think 0, think minus 2, just verify 0, then 0, 2, 0, minus 2. Okay, say I think minus 2, 0, 2, and 0. Last one, 0, minus 2, 0, plus 2. So this is our addition. Though this part is over, this calculation is over. Now we have to subtract p into I from this. So here p is equal to 2, so we have to subtract a matrix that is 2, 2, 2, 2 4 times, and all others 0. Like this. So if you subtract, what will happen? These diagonal elements get replaced by 0. Okay, so finally the W that will be zero, 0, 0, 0. So what was number here? I think it was 0. Just verify this. So whether my calculations are correct or not, how to check? First thing is that all diagonals must come 0, so they are coming, and off diagonal elements must be symmetric. So you can check here, this was 0, so this is 0, this is minus 2, this is minus 2. I think it's correct. Then this is 0, 0, 0, 0, minus 2, minus 2, 0, 0. Okay, I think it's correct. So this is the final W that you will place here. Okay, and that's it. So this network designing is very simple. You can do within few steps. Just do this simple calculation. Okay, so then you can use this, and you can verify that we have stored these two patterns in this circuit. Now, what is capacity of Hopfield network? So you can see the literature. There are many researchers who have analyzed this network. What is capacity of this network? How many vectors I can push into such kind of networks? So this formula that is derived by scientist Amit is like this. So it is n divided by 4 log of n. So C is the capacity is less than. So C is in the range actually from this to this. So this is the upper bound, max I can have, and this is the minimum I can have. Suppose n is equal to 100. If there are 100 neurons in my circuit, then how many vectors I can push? So for 100 neuron network, you can see the calculation. It is 5 to 10 or at the most 11 vectors I can store. So that way capacity is very small. So you can push only 5 to 11 or like that network, say vectors in 100 neuron networks. If you want to push more, then you have to increase this n. Okay, so you have to increase the neurons or nodes in our circuit. So as this n grows, your capacity will grow. So this is Hopfield auto associative memory. So it is recalling itself. Vector is recalling itself. So you can take take the advantage that you will feed a distorted version of a vector and get back clean version. Okay, suppose I am saying that this 4 pattern is stored in the network. This is a clean version, and from your environment, suppose you get, say, maybe a distorted version like this, then when you iterate, your network will come out with this image, the clean stored image. So this some kind of distortion, maybe noise added here, will be clean, and you will get a good representation of what you have. So this is the application of Hopfield. Now remember once again that this was vector V, and it is associated with its own copy. Okay, so V1 is associated with V1, V2 is associated with V2, and so on. Now, this is the advancement of Hopfield called as bidirectional associative memory. So it is heteroassociative content addressable memory. Earlier it was auto-associative, that means, as I said, V1 is associated with V1 itself. Now here, that is not the case. You can see at the bottom that vector A1 is associated with vector B1. So here it means that length of A vector and B vector is not same, or need not be same. Okay, so length of two vectors need not be same. If that is the requirement, then I should go for BAM. BAM means bidirectional associative memory. When vector is associated with itself, it is auto association. When it is related with something else, then it is heteroassociation. Now this is also a feedback network, but there are some changes here. It's a two-layer network. Earlier it was single layer. Hopfield network was single layer feedback. Now this is two-layer feedback. You can see here this is layer A and layer B. There are two, obviously there are two weight matrices associated with this. So this is W transpose. So this is W and its transpose. So there are two matrices, and important thing is the length of the two associated vectors are not same. And again, neurons are assumed to be bipolar binary, same as Hopfield. That means activation function is sine function. So all the vectors that we store are of this form. Say maybe you have +1 or -1 like this. All these individuals are +1 or -1. It's a binary thing. And these things are having sine functions. So all these are having activation functions which are sine. Okay, so this is the basic structure. Now what is the working of this, how it works? Here one more important thing you can note is this self feedback connections are allowed. So in this circuit, self feedback is not a problem. Okay, self feedback do exist, and you have two layers. So initially I can say I want to say have some output for pattern A. Say A is connected here. It will be passed to this W, through this W to next layer. So here net is computed and it is passed through some activation function here, and output is available here. This output is fed back like this and passed through W matrix. Net is computed here and again it is passed through the sign function or activation function of this layer. So again a new A is computed and procedure is repeated till outputs are settled. So slightly modified, but it is associating two vectors which are of different lengths. So you can see here first forward pass. Suppose I start with initial vector here. I can start with A0 or I can start with B0. It is up to me now. When I supply A0, my network will settle to associated pattern B0. When I supply network B0, it should return me A0. That's why it is called as bidirectional. So you can start with this layer as your input. You can feed back, or you can start with these vectors and you can move forward and get a feedback. So anything is possible. Okay, so there is one more diagram you can draw with this bomb. You can draw like this. Suppose these are n elements here, 1, 2, all are say A's, A1, A2 up to AN. Then you have B1, B2, B3, and so on up to Bm. Then you can draw network like this. So it's a short version to draw. So I'm drawing arrows in both directions. That means it's a bidirectional connection. You can move forward, you can come back. Okay, like this. Okay, so you can see here first forward pass, it is from B to A. So B is suppose given to you, say this vector is say B0. So whole this B0 is fed back. B0 will come here. It will get multiplied with this W. With this W. So the net available here for all these neurons is given by WB0. So that will give you net vector at point say A. So this input side is suppose A, then it is net A that is for all A neurons. So this is the net. Now if I pass through activation function, so output is A1 equal to say sine of WB0. Okay, so that is available here. Now this A1 vector is processed through next matrix, that is W transpose. So you can see here W transpose A1, that will give you net value for neurons which are here. Okay, so let me rub this thing. So nets here will be calculated in one step just by doing a simple operation. You will take W transpose, the weights here, you will multiply with A1, so that will give you directly net vector for all neurons B. Now that you will pass through again sine function, so that will give you B2, which is sine of W transpose A1. Okay, and this is the step. So this is first forward pass. Okay, you start with this B available here, you pass through this, then you pass again. So you got now new B, that is B2. So you can further process by taking this new calculation back. Okay, so that will give you new A, and again you pass it on and you will get B, again you pass on. So this procedure will continue till A's and B's are not stable. So vector A obtained say here and vector B obtained at this position, if they are not changing after certain iterations, then you will stop. Okay, so if you start with vector A, you should settle and you will get vector B. If you start with B, then you will get settlement at A. Okay, so if you supply A, you will get B. If you supply B, you will be retrieving A. So that's why it is called as bidirectional. You can use later on, once this network is trained, you can start with A, you go to B, or you start with B, you go to A. So that is possible. You can move in forward direction or you can move in reverse direction. Both things you can retrieve using this circuit. So in next class, we will see, I think with some example, how we can proceed. So let us stop here.